let's talk about something huge, but also kind of simple. Why is our planet striped? I mean, when you think about it, from lush rainforests to bone-dry deserts, Earth's climates aren't just random splotches. They're organized in these really distinct bands that circle the entire globe. Seriously, have you ever just spun a globe and wondered why all the big rainforests, the Amazon, the Congo, the ones in Indonesia, why they all seem to be hugging the equator? And then, just above and below them, boom, you get these almost perfect lines of desert, like the Sahara and the Australian outback.
Well, if you're thinking that can't be a coincidence, you are absolutely right. It is not.
What you're actually seeing is a beautiful, really elegant global system. You can think of it like a massive engine for our atmosphere, and it's all powered by one single colossal furnace, our sun. So today, let's break down exactly how this whole thing works.
Okay, so our journey starts right at the equator. This is basically the planet's engine room. It's where all the action kicks off. Now, scientists have a fancy name for this, the intertropical convergence zone. But all that really means is that this is where the sun's rays are most direct. They're just hammering the Earth with maximum power. And all that intense heat creates this belt of low pressure that wraps around the entire globe. And it all happens in a pretty straightforward four-step process. First, that super intense sun heats up the air. Second, that warm, moist air, because it's less dense, just starts to rise way up into the atmosphere. Third, as it gets higher, it cools down and the water vapor condenses into clouds. And the fourth step, the result is a ton of rain. I mean, heavy, predictable daily rainfall. And this constant cycle, heat, rise, rain, repeat, it creates the absolute perfect conditions for life to just explode. It is the reason we find the planet's great, lush, tropical rainforests right here along this equatorial belt. So, if you remembered just one thing from this part, make it this simple formula. At the equator, rising air equals high rainfall. Hold on to that thought, okay? Because it's the key to understanding everything else. All right, so you know the saying, what goes up must come down. The air that rose at the equator doesn't just disappear into space. It gets pushed outwards towards the poles. And eventually, it sinks back to Earth, creating this kind of great atmospheric squeeze. And this creates the complete opposite effect. At the equator, we had rising air, low pressure, and rain. But around 30 degrees latitude, both north and south, we get sinking air, high pressure, and almost no rain. Here's why. That cool, dry air from high in the atmosphere starts to sink. As it descends, it gets compressed and it actually warms up. Now here's the critical part. Warmer air can hold more moisture. So instead of releasing water, this sinking air is actually thirsty. It effectively sucks up any available moisture, which prevents clouds from forming. And this is why the world map looks the way it does. This zone of sinking dry air is precisely where we find most of the world's great deserts. The Sahara, the Arabian, the Kalahari, they all sit at roughly 30 degrees latitude. So our second key formula is the mirror image of the first. Sinking air equals low rainfall. And with just those two principles, we've explained the planet's first two major stripes, the rainforests and the deserts. But the pattern doesn't stop there. Let's move further away from the equator, up to the mid-latitudes, around 45 to 60 degrees. This is an atmospheric battleground where completely different air masses collide. Here, you've got warm air moving up from the subtropics, and it runs head-on into cold, dense air sliding down from the poles. When they meet, they do not mix well. Instead, the lighter, warmer air is forced to rise up and over the heavier, colder air. This process is called frontal lifting. And what did we learn about rising air? It cools, it condenses, and it creates precipitation. This atmospheric collision is exactly why regions like Western Europe and North America's Pacific Northwest are known for their significant rainfall and often stormy, unpredictable weather. For our final stop, let's head to the ends of the Earth, the poles. Here we find a fascinating paradox. These regions are covered in ice, yet they are technically deserts. How can that be? Well, it's icy for the obvious reason. It's incredibly cold. But it's a desert for the same reason the Sahara is a desert. Sinking air. The air at the poles is frigid and dense, so it sinks. This creates a high-pressure zone that, just like in the subtropics, prevents clouds from forming. Plus, extremely cold air simply cannot hold much water vapor to begin with. So what this means is that even though there's an immense amount of water locked up as ice, very little new precipitation, snow, or rain actually falls there each year. In fact, Antarctica is the largest desert on Earth. Wild, right? So from the steamy equator all the way to the frozen poles, this elegant, predictable system of rising and falling air is what draws the stripes across our planet. The entire pattern is right here. At 0 degrees, rising air creates low pressure and rainforests. At 30 degrees, sinking air creates high pressure and deserts. Up at 60 degrees, colliding air is forced to rise, creating another wet zone. And finally, at 90 degrees, that cold, sinking air creates the high-pressure polar deserts. It's just a perfect repeating pattern. This global circulation is the master architect of our planet's biomes. But it's not the only force at play. It begs the question, what happens to this perfect system when a massive obstacle, like a mountain range, gets in the way? That, however, is a story for another time.